Great. Thanks very much, and thanks for the organizers for bringing us together for this occasion. So I'm going to be talking today about some older joint work with Mike Schulman. This contains in a paper from 2017, but ever since then I've considered it an open expository problem how to talk about this. The thing that I find difficult to explain is, firstly, this is going to be some synthetic mathematics. This is synthetic higher category theory, specifically synthetic infinity one category theory. The idea of synthetic mathematics is pretty unfamiliar outside this room. It involves infinity categories, which are, of course, terrifying, and it also involves some computer formalization. So what I'm going to attempt today is, what frustrates me about this is the whole point of applying synthetic mathematics in the area of higher category theory is that higher category theory could really use it. The sort of traditional analytic proofs are quite long, quite technical. It's very tempting to skip a lot of the details. And the details, leaving them off on paper, creates impediments. A certain reader will either be comfortable skipping over the details or have the time and patience and energy to fill them all in themselves. Other people are just sort of put off the field altogether. And sort of nobody likes it either, because the way that an expert who's familiar with infinity categories thinks about them really is sort of more synthetic, maybe not quite in the sense that we're talking today, but certainly more in the spirit of the proofs today. So what I would like to focus on when I talk about this area are sort of actual definitions, actual proofs, actual ideas, and less about the technical setup. And it seems that I only ever have time to talk about the technical setup. Anyway, today we're going to try to do better. For those who've seen this talk before, I'm going to focus on this as a synthetic introduction to ordinary one category theory, because this system also has semantics in a setting where it can be understood as developing the theory of strict one categories. In kind of the simplest semantics that I have in mind, this is really an approach to evil category theory. Evil involving a sort of equality of objects, but a lot of folks' first introductions to category theory is evil, so I've decided that that's okay. That's something we can live with. All right, anyway, I'm going to go ahead and begin, but except to say that I'm particularly interested in feedback, because this is an open expository problem, from people who have not seen this before, and particularly if the category theory is a little bit rusty, because this is meant to be sort of an introduction to category theory, though from a quite different perspective. Okay, so because of this room, I do have a big advantage in describing the setting. So, another obstruction is that this is going to be within type theoretic foundations, but that's not as much of an issue here. So the setting for the whole talk is Martin-Liff-dependent type theory with function extensionality. And then there's a choice in two interpretations of the identity types. So if identity types are propositions, in the hot community we call that extensional. I've heard that's not always the right term. Then I'm thinking of this as being a synthetic approach to strict one category theory. A one category is just an ordinary category, and if you don't know what a category is, I will give a definition. Alternatively, we can use intentional identity types, maybe also the univalence axiom, though actually it's not used in this paper, in which case this is a synthetic approach to infinity one category theory, and that's how this was originally intended, but I'm really going to hide the second perspective today and focus on the first. So we're just working in the setting of Martin-Liff-dependent type theory, but there's one more ingredient that I need to add to Martin-Liff-dependent type theory. So if you're formalizing this, for instance, in AGDA, as Ingo taught us yesterday, you need sort of to work in the presence of the following structure, which is in, the axiom is a directed interval. So this is quite similar to cubical type theory, if this is something that you've heard of, except for the interval there is typically undirected. It has some sort of reversal operation. Here our interval is directed, so I'll use different notation for this. So this isn't quite the approach we take in the original paper, but today I'm going to invite you to think of this as a type that comes with two constants, so a 0 and 1, and then an binary predicate, an inequality predicate, satisfying the strict interval axioms. So strict interval is a term used by Riehl. I'm going to mention a result of him. Strict interval axioms. So the interval axioms say that this defines a bounded linear order where 0 is the minimum element, 1 is the maximum element. So we have reflexivity, transitivity, anti-symmetry. 0 is the minimum, 1 is the maximum, and then the strictness refers to 0 not being equal to 1, though you could admit the case 0 equals 1, in which case the whole theory becomes trivial. So those are the strict interval axioms. Okay, so that's the setting that we're working in, and maybe a natural question is sort of what is this for? So we have Martin-Wolf-dependent type theory. We have an axiomatic directed interval that the Blackboard 2 is a category theorist notation for the walking arrow. So that's how you might think about it, where 0 is the source and 1 is the target. Let me, in fact, draw that as a picture. So what this is used for is defining other types, which are called the simplices. So we define a family of types, naturally numbers indexed family of types. So for each n and n, we have a type that I'm going to denote by delta n, where delta n is called the n simplex. And we can define them as follows. So delta 0, I'm going to identify with the unit type. Delta 1 will be another name for the axiomatic directed interval. And for the higher simplices, we're going to embed them in Cartesian powers of the directed interval. So it's kind of easiest to explain the idea if I sort of present this as a subtype. So of those terms in the n-fold Cartesian product of the directed interval with itself, satisfying a certain predicate, which let me just express in this manner. So where the first coordinate, t1, must be greater than or equal to the second coordinate, which must be greater than or equal to the third coordinate, which must be greater than or equal to the fourth coordinate, and so on down to n. Okay, so let me draw a picture of this. So delta 0, again, is just a point. Delta 1 is, we think of as the directed interval. We could identify it with its sort of coordinate. So delta 2, I'm going to embed inside the product of the directed interval with itself, and if going to the left going to the right is the t1 direction, and going to the up is the t2 direction, then the region that defines delta 2 is here. So this is the sort of subshape of this Cartesian product that is the 2 simplex. I guess maybe I can color all these simplices in yellow. And that's the sort of reason, by the way, that we sort of swapped the order of the coordinates in depending this inequality relation. So as the other coordinates are held constant and t1 varies, we walk along the first arrow of something that's called the spine of the 2 simplex. And then as the other coordinates are held constant and t2 varies, we walk along the second arrow, and so on and so forth. So I'll draw t3 as well. This lives inside the 3 cubes, so the threefold Cartesian product of 2 with itself. And starting from, say, 0, 0, 0, we move first in the t1 direction, and then in the t2 direction, and then in the t3 direction. And the 3 simplex is the subshape of this cube that's carved out by that region, so by this sort of plane. Okay. And I guess it's sort of traditional in when working with simplices to regard the vertices of a simplex as, I guess these are simplices as used in higher category theory as opposed to as used in algebraic topology or something, though this perspective on simplices is often also used in algebraic topology. In any case, it's traditional to regard the vertices of a simplex as being totally ordered, numbered 0 through n in the case of the n simplex. And so this is the ordering given here, 0, 1, 2, 3, moving in the direction that changes the coordinate t1, then t2, then t3. Okay, so from the axiomatic structures of this directed interval, I can define this family of types called the simplices, and I can also define some maps between them. So I want to mention 2 different types of maps. So firstly, let me actually jump over here. So for n greater than or equal to 1 and I between 1 and n, I have the ith projection. So that I can regard as a map. I'm going to call it sigma I from 2 to the n to 2 to the n minus 1. So these, again, are just iterated products. And so this is projecting away from the ith variable. And this restricts to define a map, which I'll also call sigma I from the n simplex, which I think of as contained within the n cube, to the n minus 1 simplex, which I think of as containing with the n minus 1 cube. So for instance, from the 2 simplex to the 1 simplex, I have 2 different projections. One projects away from the t2 coordinate, and the other projects away from the t1 coordinate. So I have 2 maps from the 2 simplex to the 1 simplex. And then similarly for n greater than or equal to 1 and j between 1 and n, where here I'll use a strict inequality, I have a map that duplicating the jth variable. So this defines a map delta j from the n minus 1 cube to the n cube. So here my variables are in order. If I take the jth variable and I duplicate it, now I started with n minus 1 variables, now I have n variables, and again this restricts to define some maps delta j from the n minus 1 cube into the n cube. So for instance, from the 1 cube to the 2 cube, I have exactly one of these maps which duplicates this variable t, and it's going to pick out the diagonal edge in there. And so these are sometimes called degeneracy maps. The first one, degeneracy maps. These are called face maps, and there are 2 additional face maps. So in addition, I have maps d0 and dn. Here the notation at the level of the cube doesn't make sense, but it's this is all traditional notation in the setting of simplices, where d naught includes the face. So d naught is going to be the map from the 1 simplex to the 2 simplex that includes this edge that's opposite the face 0. That's the edge where the first coordinate is constant at 1. So this includes the face T1 is held constant at 1. And dn includes the face. So these are some of the face operations between cubes. What is it? Tn is held constant at 0. So the first face held constant at 1, the second face held constant at 0. And so now I have, in summary, I have face maps which get denoted, maybe I'll say dk from delta n minus 1 to delta n, but now k runs between 0 and n inclusively. And moreover, this generates a category that's called the simplex category. So if I take so there's a category whose objects are the simplices for n greater than or 0, and whose morphisms are generated by these maps. So there's a more elementary description of the morphisms from the n simplex to the m simplex that I'm not going to tell you about, because either you know about it already, or if I gave it, it's a little more difficult, or it's a little less obvious how it connects to this. This is sort of presenting the maps between the simplices using the interval representation of Riehl, if that's an idea that's familiar. And if not, that's why I'm not explaining what they are, but these are the maps that we'll actually use. Okay, so what's the story so far? So working in Martin-Luft-dependent type theory with an axiomatic directed interval, I have a family of types and some maps between them, and I've built, I guess as a subcategory of the category of types, so with types and functions, I've built this category called delta. Now I'm going to mention a theorem that connects this to the traditional semantics, so traditional approaches to category due to Andre Riehl, which is that the classifying topos, so I'm in a setting where I've axiomatized having a strict interval. So the classifying topos of the strict interval is the pre-sheaf category given by this category delta, is the category of simplicial sets. So set valued pre-sheaves on this category that I introduced. And I'm not going to say too much about semantics, but except to mention now, so I've described that everything that I'm saying could be interpreted within an extensional form of Martin-Luft type theory, where equality is a proposition, in which case so if I'm taking the extensional approach, in which case I'm attempting to do strict one category theory, I can think of this as defining one categories within the category of simplicial sets. So as we'll see, we'll be identifying categories with something called their nerves. Or if I take this intentional approach, in which case we're developing infinity one category theory, then I'm just going to replace set with a hot model. And maybe for concreteness, we want a model of homotopy type theory in spaces. And then I'm taking, again, simplicial objects, where this sort of delta variable comes from the fact that I've postulated on top of my Martin-Luft-dependent type theory a directed interval. OK, so that was the end of the first part on the setting. Any questions? Yes? I think so. Yeah. Great. Yes, that seems right. OK, this is in McLean-Murdyke, by the way, the one category result. Yeah. yeah, even a non-topos theorist was able to follow the proof. So, I mean, it's essentially just giving this construction of the simplices. That's sort of the, great. Other questions? Yes?
About the interval axioms, maybe I didn't hear it.
Sure.
Do you have any density axiom among the interval axioms?
So I intend to say 0 is not equal to 1. And anti-symmetry, so x less than or equal to y and y less than or equal to x implies x equals y, and total order as well. I might not have mentioned that one.
But you don't require that between any two elements there is another one?
No. No. Yeah. Yeah. Great. Right, so this idea of like having a coordinate that goes from 0 to 1, it's just an idea. But it's used to define these maps. So these maps I'll think of as here is being defined as functions on these types, where I define a function by the sort of coordinate encoding. So, yeah. Other questions? Okay, great. Let's do some category theory. So I'm going to adapt the perspective again, or the terminology slightly, to emphasize this extensional setting where we're developing the theory of strict categories. So in particular, if you look at the formalizations, which are based on the sort of homotopy type theory interpretation, the terminology will be slightly different, but it should be easy enough to follow. So essentially what we need to answer is the question is sort of, what is all this for? So, I mean, one setting of what this is for is to define the simplices, but what are the simplices for? And it's to allow us to probe the category structure of an arbitrary type sort of from the outside. So a map out of the directed interval will represent an arrow in the category, and that's actually the first definition. So let C be any type with terms x and y of type C. So I'm going to define a type, or really I guess I'm defining a type family. So maybe I didn't need to declare my variables there. C x, y. So I'm defining a type family over a type C as follows. So C x, y. So this is a traditional notation used in category theory for the type of arrows between two objects in a category. And an arrow is going to be given by a map from the one simplex, which is the same thing as the directed interval, into C, so that when so one of my terms of type delta 1 is 0. So I can evaluate my function f at 0, and I want that to equal the point x, so using the identity type. Or I can evaluate my f at the other endpoint 1, and I want that to equal y. So this type here is just the type of kind of the free living arrows in C. This is the type of arrows with specified source object x and specified object y. Okay. So I guess there's one thing that I should say is that actually the type theory that Mike and I introduced in this paper is a bit more elaborate than this, because we want to be able to work with a simpler definition of these types. So there we introduce something called extension types, which allow us to, I guess, so what have I done here? So in the, let me just work in the extensional setting, which is kind of where I'm focused today. So this can be regarded as sort of a subtype of the type of functions, just from the one simplex into C. What an extension type would allow us to do is define this to be the subtype where these two equalities hold judgmentally and not just using identity types. For formalization, this is a huge convenience, and it's going to be reflected on the board today, where I am a little bit sloppy with this sort of data. So often I'm going to have to either supply that data or project away from that data, and I'm not going to do that in the functions because in the formalizations that are in this proof assistant RZK, the first link above, we have extension types, and that data is not there. So there's a computational layer of the proof assistant that is checking these boundary conditions and assuming that you've defined things correctly. There's no proof obligation to supply them. But I'm trying, again, to work in a more familiar setting, so we're not mentioning extension types today. And this type is equivalent to the extension type. It's sort of the difference between having a strict fiber of a fibration and a homotopy fiber, which, if we're doing pen and paper mathematics, is maybe no difference, but in formalization it does simplify things. Okay, so what I can do with the Hom types is I can define which types are synthetic categories. So by probing with the Simplices, I guess you could think of each type as being something like a quiver or a directed graph. It has its objects being just the terms of the type, and it has these arrows, which are maps out of the one simplex. This type family sort of partitions them into families with specified source and target. So a type C is so I'm just going to say category, but I should think about this as being a strict one category, or in the infinity setting, I would call this maybe a pre-infinity category, but today I'm just going to say category. So a type is a category exactly when if composable pairs of arrows have a unique composite. Pairs of arrows have a unique composite. Okay, so what do I mean by this? So first, let me draw a picture. So if in my type C I have x, y, z, I have free terms, and I have f and g, and again, what I mean by this is I'm saying that f belongs to Hom C x, y, and g belongs to Hom C y, z. So I have a pair of arrows, and what makes them composable is that the target of the first arrow is equal to the source of the second arrow. What is a category? A category is some sort of quiver or some sort of directed graph with composition, so I should then be able to specify a unique composite arrow like this. And sort of the innovation in this setting is to regard this data as not just sort of three arrows satisfying some conditions, but the fact that this diagram commutes in the language of category theory is given by some data. So all of this is given by a two simplex. So the way that I make precise this condition that composable pairs of arrows have a unique composite is as follows. So the type of composition data inside my type C involving an arbitrary composable triple of arrows is just the function type from the two simplex into C. So recall this is our picture of the two simplex. This will specify three terms in C, the image of these three terms, 0, 0, 1, 0, 1, 1. It will also specify arrows between them, and this higher stuff is how I think of encoding the composition relation. So then there is a map from here to the following type. So this is going to be the type given by two different arrows. So f from delta 1 to, I guess I can just do them both here, f and g from delta 1 to c, so that f of 1 is equal to g of 0. And there's a map here that I can define using these maps between the simplices that I mentioned previously. So if alpha is a function from delta 2 to delta c, I can pre-compose it with some of these face maps. So those will be maps in the setting from delta 1 to delta 2, and then I'll get a pair of maps from delta 1 to delta c. And the two face maps I'm supposed to take are delta 2 and delta 0, and then there will be some proof that shows that that condition is satisfied. In this case, this is a consequence of some of these relations between the maps and the simplex category that I did not mention there. So there's a particular map like this. This proof would not work if in general, if I took any other pair of face maps than the one that I indicated. This idea is due to Siegel. And what it means for a composable pair of arrows to have a unique composite is that this map is an equivalence, or maybe I should say it's an isomorphism if I'm talking about extensional type theory. I'm not sure what terminology is typically used. So an equivalence between types.
Excuse me, why don't you make it primitive, a primitive composition? You want that?
Yes, this is much better. So I love that question. So this is weird. So this is not the usual definition of a category, and let me work towards the usual definition of a category. So the usual definition of a category is I start with a directed graph. So maybe the slogan is that a category is a quiver. Do people actually use the term quiver? I never know. Yes, okay, is a quiver, a directed graph with unique functional binary composition. I mean, that's not really the definition I gave. Instead, I'm talking about some weird Siegel map being an equivalence. But the first thing I can extract from this is a composition function, and then I'm going to return to your question. So if C is a category, then for any triple of objects, X, Y, Z, and C, triple of terms, I can define a map, which I'll call composition, using infix notation from Hom C YZ to Hom C XY to Hom C XZ. So this is the signature of the usual composition function associated to a category. And how is it defined? So I take an arrow G and F to, so from my G and F, so there's an equivalence that I did not mention. Again, I said I'm going to be sloppy about these proofs of equality because in this extension type setting, they're not there. So this pair, which lives in the product of these Hom types, defines a term of the sort of codomain of this Siegel map. So if I take the Siegel map inverse of my pair FG, now I have a map from a 2 simplex into C, and I can precompose with the third face map that exists between the 1 simplex and the 2 simplex and extract the composite edge. So by pairing these up, I'm forming something that's called a horn in here, and then I'm restricting to the other. Then I use the Siegel map to extend this to a 2 simplex, and then I'm restricting to the other face of the 2 simplex to define the composite arrow. So this is the composition function. So indeed, I do get the data of a composition function out of this funny definition of a category. But why is this a good definition? I mean, the reason it's a good definition, there's a couple different reasons. So one is that I get to stop here. So the usual definition of a category requires additional things. So firstly, I need identities, then I need associativity. I don't have any of that. In fact, I'm going to prove it for you momentarily. But this idea of sort of using the higher structure, by which I mean probing from these higher dimensional simplices into C to encode category structure, is sort of very powerful. What we'll see is that sort of functoriality and naturality come along for free because of this. Whereas if my definition started with a quiver and then provided the data in this form, then associativity would be a further axiom, identity would be a further axiom, functoriality would be further axioms, naturality would be further axioms, and all of this comes for free in the synthetic setting. Okay, I don't want to say so much about the semantics, but for those who are familiar with categories, this is a natural point for skepticism that this is even a definition of a category. And so maybe I'll just mention as an aside a proposition of Riehl about this sort of strict one category semantics in here. So let me just say that so in that semantics, you can think of types as being a simplicial set. So a simplicial set C is isomorphic to the nerve of a category. And what I'm referring to here is that there's a canonical functor from the category of one categories into the category of simplicial sets. And so I'm identifying its essential image, a fully faithful embedding, sort of if and only if. So the semantic interpretation of this map is as follows. So the category of simplicial sets is Cartesian closed. We usually use exponential notation for function types. And this more complicated thing is equivalent to maps from some simplicial set that's the 2-1 horn into C. What I'm asking here in this extensional type setting is that this map is an isomorphism in the category of simplicial sets. And that particular map being an isomorphism forces the simplicial set to be a nerve of a category. So that's the sense in which this does capture exactly the categories embedded in our semantic setting. If that didn't make any sense, this is just to help folks who are skeptical believe this definition. Okay, but again, I'm trying to take a more elementary point of view. So we have a pretty funny definition of a category. And in one sense, it's really prioritizing composition. I mean, if you've ever had the experience of explaining categories to non-mathematicians, this is the thing you say. It's just all about composition. You take a directed graph and you add composition, and that's a category basically. But for those of us who remember the definition, you might ask sort of what about identities or associativity, sort of the rest of the usual category axioms. And the point is they follow. In fact, maybe I can stick identities here, so why don't we do this before we leave it. So this definition actually doesn't require C to be a category. So for a type C and X in C, I can define a term, the identity of X in the Hom type from X to X. So let me just recall again, this was defined to be the type of maps from the one simplex into C, so that f at 0 is equal to X, and f at 1 is equal to, in this case, X as well. And that permits me to define the constant function. So T maps to X, refl is a term of this type. This is exactly like, for those of you who were in the AGDA tutorial yesterday afternoon, the way the reflexivity term was defined in the path types there is exactly the same. So constant functions define identities. Oh wait, I'm not supposed to do that yet. So I'll leave as an exercise the proof that if C is now a category, so satisfies this definition of composable pairs of arrows have a unique composite, then for any arrow f from X to Y in C, so in a category, from my axiom, I can extract a composition function. And using the composition function, I can make sense of f composed with the identity at Y. And the thing that I can prove is that that's equal to f, equality inside the type of arrows. And also f is equal to the composite of f with the identity at X. So the unit laws can be proven from that definition here. The reason I'm leaving that as an exercise is I want to prove instead associativity, which I think is kind of more illustrative. So again, if C is a category, and let me give the context by drawing a picture. So a category with terms W, X, Y, Z, and arrows F, G, and H. Then H composed G composed F is equal to H composed G composed F. Again, I'm using the identity type associated to the Hom type, in this case from W to Z. Okay, to prove this, I'm going to use another result. So the proof uses a further proposition, which is that if C is a category and X is a type, then the function type from X to C is a category. The reason is a type is a category when some canonically defined map is an equivalence. And if I take that equivalence and I exponentiate with x, and then I commute some stuff, do some Fabini thing, I get the corresponding map for the function type. And so that's then, again, an equivalence. OK, so now let's prove associativity. Proof of associativity. So I'll apply this proposition in the setting where x is the one simplex. So the type of all of free-living arrows in C is a category. So my hypothesis is that C is a category, so the type of functions from the one simplex into C, the type of arrows in C is a category. So I can consider a composable pair of arrows in here, and my axiom is that I have a unique composite. So my composable pair of arrows involves 3 objects. These objects now all live in the arrow category, and the objects are given by my 3 morphisms. So this is going to be a picture, again, in arrows in C. So I have 3 objects here. Now I'm going to define a composable pair of arrows, so an arrow from the first object to the second object, firstly. And so that is going to be a map from delta 1 into delta 1 to C, which by currying is a map from delta 1 cross delta 1 into C. And it has the following form. So it's given by the data of some 2 simplices. So using the fact that C is a category, I can take my F and G and I can compose them. So using the inverse of the Siegel map to define a 2 simplex whose diagonal arrow is the composite. I use that twice, and that gives me a map from delta 1 cross delta 1 into C, which is my first arrow. And then I do the same trick with G and H to define my second arrow. And so this is now a composable pair of arrows in C. And then if I take Siegel inverse of this composable pair of arrows, that now gives me a map from delta 2 into delta 1 to C. In other words, from delta 2 cross delta 1 into C. So I get to fill this in to define a prism. So that's adding, among other things, these back edges. And in simplicial sets, delta 2 cross delta 1 is a simplicial set that's sort of triangulated. It has 3 simplices inside it. And the one that I want to isolate in particular is contained here. So it contains that data plus a new diagonal edge, which I'll call D, plus 2 sort of back faces. So what I've highlighted here in yellow is a 3 simplex that's a subshape that's sort of a restriction of the data that I have here. And in particular, if I look at the back 2 faces of this 3 simplex, I have a 2 simplex here and a 2 simplex here. So this first 2 simplex has, as its boundary edges, F followed by H composed G, and then the diagonal is called D. So using the fact, really, I guess all I've used so far in the category axiom is that this Siegel map has a map in the other direction called Siegel inverse. But now I'm actually going to use that this is an inverse pair of equivalences. So from just the presence of a 2 simplex, which I guess I'll extract and draw like this, which involves the edge F followed by the edge G composed H, and the fact that I'm in a category, I get to conclude that this composite is equal to the diagonal edge. Why is that? So in my category C, I have a pair of 2 simplices which have the same horn. So I have the sort of specified composite. This is Siegel inverse of that composable pair of arrows, and I have the 2 simplex that I extracted here. These are 2 terms that live on the left-hand side of that equivalence that map to the same thing on the right-hand side of the equivalence. So because it's an equivalence, they're equal. and then I project that equality off, and that gives me this one. So similarly, using the bottom face here, I have, involving the same diagonal edge, another 2-simplex witness like this, and I have, of course, also my specified composite of this composable pair of arrows, which has this following form. And so then I get to conclude also that D is equal to H composed F. And so that's the proof of associativity, and what it's illustrative of, so there are various results that I did not prove, is that they all have this sort of higher dimensional nature. Okay. Great. So, right, so I've given some justification for this synthetic definition of a category by showing that from one axiom that's a little bit less familiar, I get at least the full category axiom, so maybe that's good. But really the sort of power of this setting comes from the final result, and I think I'm just going to jettison the third part of the talk and end here. So, which is the following. So in the synthetic setting, functoriality is for free. So let me give a definition. So the definition as follows. If C and D are categories, then a functor, so functor is the term used for functions between categories, and literally that's going to be the definition here. So a functor is a function between the types. So categories are types satisfying a certain condition that composable of pairs of arrows have a unique composite. I'm going to define a functor to just be a function like this. So again, that's an appealingly simple definition, but what does it have to do with functoriality? So question, sort of where is functoriality? So, so usually if I'm describing functors between categories, there are two functoriality axioms. The first one would be something like f of an identity is equal to the identity. So sorry, the first thing I should say is that having maybe a basic observation is, a function between types certainly defines a mapping on the terms. That's the whole point of it. So that's one bit of a functor. It has a mapping on objects. But it also automatically encodes a mapping on arrows, because remember, my sort of Hom types are subtypes of arrows. So if I'm have Hom C xy, which I'll remind you is the type of maps f from the one simplex, so that f0 is equal to x, and f1 is equal to y. So I'd like from f, so given a functor, I'd like to have a map from this to the Hom type of D from f of x to f of y. And how is that defined? So that takes my f with two proofs, p and q, and just sends it to f post-composed with the functor, and then I apply my functor to these proofs. And so I apply my functor to the proof. So automatically from this function, I get both the mapping on the objects and arrows, but there's usually a functoriality axiom. So in other words, for a composable pair of arrows, so firstly, f preserves the identities, and secondly, f preserves composites. So I'll leave this first result again as an exercise, but I want to prove the second, which is functoriality, because again, I think this is sort of the best illustration of why this synthetic definition is, in fact, a good one. And again, if I started with just axiomatically asserting the existence of a composition function, I would just have to, what I'm asking is that this function commutes. So I've defined now these maps between Hom types. This is just some square, and I would have to assert that that square commutes. There would be no way to prove that that square commutes, but I don't have to. So functoriality is for free. So given a composable pair of arrows and a functor, so between categories, so that's my hypothesis, then f of g composed f is equal to f of g composed f, using, on the one hand, composition in C, and on the other hand, composition in D. And so the idea of it is as follows. So inside C, I can build a Siegel of my composable pair of arrows, FG, and that's this 2-simplex that involves my F and my G and my specified composite. But now I can just post-compose with F, and now if I wanted to draw a picture of the composite, the terms are or the elements are fx, fy, fg. This is how I define f of f, f of g, f of g composed f. So I have a 2-simplex like this in D. But because D is a category, I also have a 2-simplex involving the composable pair ff, fg, and the composite as defined by the composition function above, are really defined by this Siegel map inverse. Sorry, this is all Siegel inverse. This is, again, Siegel inverse, but now of f of f and f of g. And again, I have two simplices that restrict to the same thing on one side, and that implies my equality. All right, I will stop here. Thanks. So, thank you.